Thank you for coming out. This talk was originally aimed at sharing our end user story as end users of the project and contributors to SPIFFE and SPIRE. Now, after chatting throughout the conference with different folks throughout the week, we feel there's still a lot of skepticism and lack of understanding, possibly even fear, doubt, and uncertainty around quantum computers and quantum-resistant algorithms. So we shifted things a little bit last minute to explain some more of the case in the background, what's the impetus behind it. I will preface with, I am not a cryptographer, but over the past year working with Hugo and closer to the cryptography community, I have come to learn the most dreaded situation for a cryptographer to be in is to have to explain the math of a crypto system to a lawyer and why is that math secure. I recently found myself, only a couple weeks ago, having to explain it to a lawyer myself. And to my surprise, he was able to grasp it, and he hit me back with a great analogy of cyber attacks used to be very much like a bank heist. Against the clock, quick, frantic, loud. They only had as much time to, detection meant failure. Now, these attacks have turned a lot like forklift jobs. The attacker lifts the entire safe, the data, the credentials, the systems, and takes it somewhere quiet. No alarms, no rush, just a slow, methodical decryption and exploitation. A blast open safe does bear a lot of resemblance to unscrambled data from a Kubernetes container. Forward secrecy protects past and future data even if long-term keys are compromised. This is especially critical in systems where confidentiality needs to last for decades, like in healthcare, finance, or defense. While current cryptographic systems are still holding strong, the rise of quantum computers could change that dramatically. Even though we don't have large enough quantum computers yet, the threat is there. A quantum computer operates over qubits. A single ideal qubit exists in a superposition of the basis states of ket 0 and ket 1. Which correspond to the classical binary bytes 0 and 1. But instead of these being just values, these basis states are actually orthogonal vectors, and they form the basis for a linear vector space. What that means is a single qubit can express any linear combination of the vectors ket 0 and ket 1. So let's look at the composition of a qubit, which we'll call phi. We will write this as ket phi equals alpha ket 0 plus beta ket 1. Although by definition, alpha and beta are called a probability amplitude, meaning their squares have to add up to 1, the qubit allows for states like ket 0 plus ket 1 divided by the square root of 2, which means it's in a state where both its 0 and 1 will equal probability, and more importantly, that property scales. Most traditional encryption today, such as RSA, elliptic curve cryptography, and Diffie-Hellman, rely on the difficulty of factoring large numbers of solving discrete logarithms. However, quantum computers can run short algorithms which can factor large numbers in polynomial time, making RSA and elliptic curve encryption obsolete. Shor remains the biggest threat. Shor algorithm was proposed by Shor in 1994, and defending against it requires a new set of mathematical algorithms. We have to diversify the set of mathematical problems. That's why the National Institute of Standards has already started standardizing quantum-safe alternatives. Of the quantum-safe algorithms, lattice-based cryptography makes for the most versatile foundation for quantum-resistant crypto, enabling multiple primitives like fully homomorphic encryption, signatures, and key exchange mechanisms. They offer strong security reductions to problems like learning with errors, and are built in linear algebra over NP-hard lattice problems, structured as n-dimensional grids, as you see on the slide. This is the backbone of schemes like Kyber and the Lithium. In round 3 of the NIST post-quantum cryptography standardization process, which culminated last year, NIST selected Kyber, ML-Chem, and MLDSA as federal information processing standards, FIPS 203 and FIPS 204. Now, breaking classical crypto might feel decades off. Right now, we would need thousands of physical qubits just to get one reliable logical qubit. And IBM thinks we might not reach that level until the late 2030s. That said, a surprise breakthrough, a black swan event, could speed up things much faster than expected. Right now, there's at least a 10x capability gap between hardware and what they need to break, what they would need to do to break modern cryptography. So we're not quite there yet. But of what makes it not quite there yet are technical hurdles like qubits not staying stable for long enough. There's a lot of errors during computation, and challenges in scaling up these quantum computer systems. We haven't really cracked quantum error correction, which is essential for making quantum computers reliable. In recent weeks, we saw Google announce Willow at 105 qubits, and that's not quite cryptographically relevant yet. We would require millions of qubits and error corrections for such a task. And the current focus is quantum error correction and scalable bits. At the same time, the expert opinion has started to shift. This is a graph from the Global Risk Institute where the surveyed experts put the likelihood at around 30% of there being a breakthrough in the next decade. That's quite serious considering attackers can already harvest data and decrypt it later. So even without a quantum computer yet, there is a threat window. The moment data is encrypted today and for the time period it needs to stay secure, and the moment in the future where quantum computers might decrypt it retroactively. So if X plus Y is greater than the quantum threat, because the data encrypted today, like consider healthcare data requiring long-term confidentiality, must stay secure for about 50 years. It will take 10 years, should they commence work today, to migrate systems to quantum-safe alternatives. If a quantum computer capable of breaking RSA and elliptic curves arrive within the next 60 years, that organization is already at risk today. But very well framed by Ryan Hurst in the cryptography community, if you handle life-critical data, you should already be taking action. If your organization deals with sensitive data that requires long-term confidentiality, you should start thinking about it today. But if you don't deal with either, chances are your organization may not face this in the time of your career. But quantum computers aside, if a quantum computer never is realized, what is the value of these algorithms given that there's enough attention to the problem? Classic cryptography has subtle implementation flaws that can lead to significant vulnerabilities. You can look at the documentation for Python's cryptography, the Hazmat module, and it has the warning of you should only use it if you know 100% what you're doing. Things like timing side channel attacks, weak subgroup attacks, or off-curve inputs. These crypto libraries often expose very low-level hazardous APIs that are very easy to misuse. It's like shooting yourself in the foot. And despite strong standards, there's many flawed implementations that remain persistent to these problems. So the merit of this newer set of algorithms lies in the diversification of problem, particularly constant timing implementations, deterministic functions like shake, which reduce the chance of failure due to poor randomness, defining sampling stops for attackers for exploiting bias, and deterministic behavior. Many of these algorithms are formally specified and formally verified. And fast key generation isn't really about performance. It also enables forward secrecy at scale. And vetted parameters prevent like do-it-yourself configurations. Secrets can be long-lived, particularly in national defense. Governments tend to work with secrets with life cycles for about 25 years. On top of that, with the grounds of store now, decrypt later attacks, meaning an adversary might store encrypted messages today that have been exfiltrated and decrypt them once they have a large enough quantum computer later. Many governments like the UK and the US have started to legislate a plan to migrate systems. This is from GCHQ only last week. NSA the last year released updates on CNSA 2.0 with the advisory to account for quantum resistant cryptography. We know cryptographic migrations tend to take a lot of time. We can look back at the SHA-2 migration timeline. And the sequencing of phases for cryptographic algorithm transition from selection and development, standardization, implementation, deployment, and usage. Where we're at today is like very early steps of implementation, but the majority of the industry is not quite there. Certainly not the enterprise. There are real-world adoption examples of key digital infrastructure. There's not an exclusive list. There are many more. OpenSSL just announced in the last week near-term roadmap for it. So how can the Kubernetes community and cloud-native community take action to prepare? It's important to limit the utility of keys to an attacker, and the key lifespan is not just about the algorithm. It largely depends on how the keys are managed. Using keys for shorted periods will reduce exposure even if those keys are compromised. Regular rotation will limit risk, but it also will help you stay prepared for transitions. Historically, as an industry, we haven't done a great job if we look at high-profile compromise like DigiNotar, Heartbleed, Storm. A lot of the key management we have in place today focuses on reducing sprawl, but not in true protection. Even if you're using hardware security modules, keys are most exposed when they're in use or when they're distributed, and that's exactly where defenses are the weakest. Cryptographic agility is about staying ahead of the evolving risk. That means being able to swap algorithms, ciphers, and protocols easily, managing keys securely throughout their life cycle, and adapting policies as standard change, and staying prepared for new cryptographic threats on the horizon. As the cryptographic right answers evolve and the use of post-quantum cryptography increases, commensurately the anxiety in the enterprise will grow. The fear is often driven by lack of clarity on what applications use cryptography and the unknown outcomes of changing algorithms and rolling keys. And that hinders adoption. Now, to overcome that anxiety, there's steps you can take. You can eliminate manual processes and remove the human from the loop. You can make use of better visibility and observability to help trust the safety of changes while standardizing the practices that make everything easier to understand and debug. And by regularly exercising those changes, you will build the confidence that teams need in order to move faster. Adam Langley's quote is a great metaphor for crypto agility. The idea is fairly simple. Instead of spreading complexity across the system, focus on a well-defined, maintainable point. One joint, well-oiled. That way, when crypto needs to change, you will have a single place to update, making your system both adaptable and secure. Key management is often treated by auditors or compliance teams as a checkbox and just rigid-based policies, but also ensuring you overcome the disconnect between policy teams and operations is critical. There are a number of operational challenges that I'm not going to cover at length, but having them on screen for you and for posterity if you want to look at it after. So let's bring it back into being a SPIFFE maintainer talk. I've used the SPIFFE throughout the last decade of my career, throughout many different organizations, and there's a number of reasons why we chose to build around it. It gives us dynamic, verifiable identities for every service. There's no more static API keys or long-lived certificates. The credentials are short-lived and automatically rotated, reducing the risk. And identities are tied to trusted runtime signals. And with SPIRE, the reference implementation, we get centralized control over the issuance, renewal, revocation, all governed by policy. When authenticating workloads, service account level trust is not enough. You need workload level attestation. You measure the code, verify the runtime behavior, possibly even tie it to trusted execution environments or policy-based context. So with that, I'm going to pass it on to Hugo and talk about the work and the approach of fitting PQC into SPIFFE and SPIRE.
Hi. So SPIFFE and SPIRE make use of cryptography in ways which require adaptation to obtain PQC security. So it's based on TLS, mutual TLS specifically, which uses asymmetric cryptography, it uses key exchange mechanisms, and it uses certificate verifiers, which is a piece of data which verifies that the counterparty controls that certificate. These are vulnerable to cryptographically relevant quantum computers, so these need to be retrofitted with new quantum-resistant algorithms in order to make mutual TLS secure in the post-quantum landscape. SPIFFE is based on TLS, it is based on X509 certificates. It can also use JWT tokens, so we need to retrofit these formats with new algorithms. So the real highest threat that is in this landscape is that of the cryptographically relevant quantum computer poses to key exchange. because this allows attackers to capture data that is encrypted now and store it on the speculation that someday in the future they may have a cryptographically relevant quantum computer, and then they can just retroactively decrypt all data that they have captured today, which means that you actually need to be thinking about this threat right now. So the absolute highest priority is to tackle the key exchange piece in the TLS stack and replace the existing key exchange algorithms such as elliptic curve Diffie-Hellman with a post-quantum secure key exchange algorithm. Of course, you also ultimately want to retrofit the signature algorithms in X509 certificates and in JWTs with post-quantum secure algorithms, but because that requires an active attack, it's less urgent. So we integrated post-quantum cryptography algorithms to SPIRE. We added Kyber X25519 hybrid key exchange, which is post-quantum secure, to the TLS stack that is used by SPIRE. We augmented X509 certificates with dilithium-free signatures, which are now the basis of MLDSA that has been adopted by NIST as the basis for authentication. So we have tackled both of these threats, both the higher priority threat and the lower priority threat. Designing for quantum security, we have now TLS with post-quantum cryptography, which can be used alongside with the filtering policies that Cilium allows to express filtering policy at layer 7, including HTTP request fragments. This enables secure cross-cluster communication. So the building blocks of SPIRE, Cilium, and Envoy to actually support the service mesh approach where HTTP requests being made over MTLS can actually be audited and inspected in terms of the URL structure to allow and deny requests at an application level based on what is in that URL. So now we have a short demo.
We didn't really plan not to be mic'd up and having to handhold the microphone, so I might put it like right here for Hugo.
Thanks. So,
we have fitted this for tactical edge equipment. We have a XR4000 and a couple gateways.
So what we have here is a 3-node Kubernetes stack running Cilium. As you can see, if I run Cilium status, we have a lot of different things running, and it's all in good status. So we have a short payload. Yeah. Okay. So if we take a look at our namespaces, we can see we have a default namespace, and we have a simple test application running in the default namespace. So if we now take a command such as this, so we've now made an HTTP request from our demo pod worker to our Temo echo server, and we can see that we just have a simple diagnostic result over this HTTP request. But if we try a different HTTP request, we can see that our access is denied. Why is this? Well, it's because we've configured a Cilium network policy, namely this, which, as you can see, restricts. If we take a look at the YAML that defines this, we can see that this restricts the HTTP requests that we are allowed to make, so that we are only allowed to make request by this URL and not to anything else. So we are allowed to impose fine-grained policy where this is not allowed, but this is. The big deal is, of course, that this is going over Envoy service mesh, so that from one node to another, this is all being secured over MTLS, which is post-quantum secure, so that your application is not required to know anything about post-quantum algorithms. The node-to-node communication is secured, and you can actually add policy on top of that. So we can also take a look at some things that show us how this is working. So for example, if I just paste in a command here, we can paste a command in here. And we can see that there is a whole process going on behind the scenes in which Cilium is interacting with SPIRE to get authentication certificates that can be used node-to-node to authenticate communications. We can also see the identities that are going on. Each node, as you can see, there's a numerical identity assigned to each workload, and this is then retrieved as an X509 certificate from SPIRE, which is used for MTLS communication. So we can also look at an X509 SVID specifically. So for example, if I take this command, so what is this going to do? Well, what this is going to do is this is going to query the SPIRE server for an X509 SVID, which is a kind of X509 certificate, and it is going to request the identity for our Echo server demo, and it is then going to decode that X509 certificate. So, what do we have here? What we have here is a new certificate which is signed. We can see that there is a SPIFFE identity on it for our Echo workload, but we can also see that the signature algorithm is actually something new. It's actually something new enough that the version of OpenSSL installed on this machine doesn't understand, so it's just telling us that it doesn't understand it and showing us the raw data, but I can tell you that it is a dilithium-free signature. So there you have it. And that pretty much sums it up.
Yeah, it's noteworthy that the support for Kyber and dilithium are part of SPIRE server, SPIRE agent configs. I don't know if you want to showcase that real quick, or could you do a kubectl edit for the SPIRE agent and SPIRE server config? We'll share the code examples afterwards, as well with the changes that were upstream to SPIRE, but I'm going to pass it back to Hugo for some key takeaways. You can grab the...
So basically, cryptographically relevant quantum computers threaten current asymmetric crypto, especially their store now decrypt later attacks, where an attack now just recording traffic that you can't currently decrypt could be decrypted later in the future. So adoption of at least post-quantum secure key exchange mechanisms is critical now to future-proofing systems like SPIFFE and SPIRE and other PKI technologies. So that is the highest risk, hence you want to adopt post-quantum secure key exchange mechanisms, particularly hybrid mechanisms such as X25519, Kyber 768, where you are actually hedging against the possibility that either algorithm becomes insecure in the future. Likewise, you will ultimately, but this is less of a priority, want to retrofit X509 certificates and JWT tokens and other things that use signature algorithms with post-quantum secure signatures. There are some gnarly parts of the TLS protocol which can result in peculiar outcomes, such as where both sides of a connection support a post-quantum secure chem, but due to slight implementation differences, they actually don't negotiate the chem. This is something to watch out for. And in this case, they end up falling back to a non-quantum secure key exchange mechanism. So you actually need to have a way to measure what you were actually negotiating in the field and verify that this is being used. So with the Go ecosystem, and of course this is highly relevant to Kubernetes, very large amounts of software implemented in Go. Go has now shipped mainline hybrid key exchange mechanisms for TLS with Go 1.23, so in many cases you can actually deploy this in your existing Go code just by upgrading to Go 1.23. For things like post-quantum signatures, we actually made an adoption based on Cloudflare's Circle, which is a library that Cloudflare pioneered for these dilithium-free signatures. The NIST standards have now been published, so you should expect a lot of churn.
Thank you for that. Security is never done, so we encourage you to start planning and considering the sharp edges, the trade-offs, the considerations to embark on migrating to quantum-resistant algorithms and working with the open source community and sharing those learnings. We would like to thank the SPIFFE and SPIRE projects as a whole, the steering committee, the maintainers, and the community of the respective CNCF projects that make part of the data path with which we showcased. It's literally taking a village, but we're very appreciative for the support and enabling us to carry out this work. At the same time, as a small business working in the front of national defense, we want to share our customers, a big sentiment of gratitude to the United States Department of Defense and our partners at the Dell Technologies Federal Team for allowing us and enabling us to carry out this work and demonstrate a feasible path that can light out an approach, again, like one joint, well-oiled, in order to bring quantum resistant sooner than would have otherwise been possibly realized had we been doing this individually and not in the open. Thank you. I think it's lunchtime, but happy to take any questions.
Thank you. I wonder if you're able to comment on the delta in overheads in running in the target state as opposed to the old crypto.
I can barely hear you with the server running by my side. Can you ask the question again, please? Louder?
Louder. I wondered if you were able to comment on the delta between the overheads in running in the target state and the previous state.
So I believe what you're talking about is the larger key sizes and traffic sizes of post-quantum algorithms, correct?
Exactly, yeah.
Yeah, so you are going to be paying a higher computational cost for this kind of post-quantum security. Everyone would like an algorithm that exists that is post-quantum secure, which is as fast and light rate as the classical algorithms, but we are waiting for Godot on that one. So you're going to be paying a higher cost, but I don't think that you're going to be really having it as a concern in practice, because the cost of the TLS handshake in a large variety of deployments is not the bottleneck in your workload, even before or after. So yeah, you are going to be seeing more TLS traffic overheads, but I think that mainly shows up.
Let me trade places with you real quick. No, go on.
But I think that mainly shows up in environments where the primary thing you're doing is terminating TLS workloads. So for example, if you have a TLS load balancer that is accepting requests from the internet and it does only this, well, for example, you're relying on that load balancer to be able to handle 1 million requests per second. If you adopt post-quantum cryptography, that may go down. But in an environment such as Kubernetes, where the overhead of a TLS connection is lost in the noise of countless other computational activities that are going on, I don't think that you're going to see a significant impact. Does that answer your question?
Yeah, thank you.
Hey guys, great talk. Thank you very much for that. I was wondering if you could help me unpack a little bit. What is it that we could do, like today, to prepare ourselves for these new breed of algorithms? Like, if NIST is standardizing and ratifying lattice-based stuff, right? Your OpenSSL version was so, that's so bleeding edge that even your OpenSSL's version on your laptop couldn't really recognize the algorithm. Is it too early, do you think? Like, all those building blocks that you've mentioned, the SPIRE, the Cilium, the, I don't recall all of them, apologies, but it seems that the stack is fairly experimental, right? So would you say that we are, like, as cryptographic, non-experts on cryptography, but someone with a vested interest on making our system secure, are we ready to even start adopting the lithium and all this lattice-based stuff? Is our stack going to break if we do that? Could you just shed a little bit of light on that?
So I think as an end user or as a system administrator or operator deploying in the field, the main thing you can really do is listen to the advice of your vendors and upgrade when they have a post-quantum story available. And if they aren't promising a post-quantum story in the future, then you should be asking them questions on that. In terms of what's available now, we're actually finally starting to see the practical viability of post-quantum algorithms in terms of existing software stacks. There's now compatibility being shipped by OpenSSL, but we've already seen, actually for a number of years, Cloudflare and Google shipping experimental versions of these algorithms in Chromium and so on and so forth. So we're now getting to the point where this sort of thing is being turned on by default. As I said in Go 1.23, you now automatically get the benefit, if you want it, of a post-quantum secure key exchange mechanism. So again, it's just a case of really upgrading your software when new versions become available, and these capabilities will be turned on by default in most cases. If you're building your own software, then you need to be looking at the SSL library you're using and really enabling that. So in Go, for example, it's literally just a case of upgrading to Go 1.23, and then suddenly this is in the box, it's automatically on. So I would say from an end user perspective, it's mainly a question of upgrade when the patch is available and really track the software that you're deploying and see if a vendor has offered you an upgrade yet.
I believe no more questions. Thank you very much.